again into the 12th science chemistry class. Now in the last lecture, up to the last lecture, we are learning about that of the different concentrations of the solutions, what are the effects of the pressure temperatures on the solution. We also learned about that is the Raoult's law, which is nothing but that is the vapor pressure of the solution is the multiplication of the vapor pressure of that solution in the pure state and its mole fraction. Now today we are learning the colligative properties. Now these properties are totally new for you. What is the meaning of the colligative property? Let us learn first. So the colligative properties of non-electrolytes we have to study in this chapter. Non-electrolyte means when the solute, which is the non-electrolyte solute, dissolve into the solvent, it does not ionize. It do not give the positive or negative ions. Such non-electrolyte solutions such as urea, that is a sugar, such as glucose, and that of the cane sugar, such type of non-electrolyte solutes, when dissolved into the solvent, they form the solution of non-electrolytes. So let us learn first about the colligative properties. Now colligative property means these property totally depends upon the number of solute particles dissolved into the solvent. That means how many number of solute particles are there, that is very important. So colligative properties are the properties of the solutions which totally depends or fully depends on the number of solute particles into the solution and not on the nature of that of the solute. So what is the definition of colligative property? The physical properties of solutions that depend on the number of solute particles. This word is very important. The physical properties of solution that depends on the number of solute particles in the solution and not on their nature are called colligative properties. Now we have to study totally 4 colligative properties. There are the 4 colligative properties. The first one is the vapor pressure lowering. Lowering means decreasing. What is the meaning of this vapor pressure lowering? The vapor pressure of the solution is lower. When lower? When we add the solute into the solvent, the solution is formed. So the vapor pressure of the solution is less or lower than the vapor pressure of the solvent when we add the solute into that. So vapor pressure lowering delta P, that is it is the difference between delta P is nothing but the vapor pressure lowering, which is the difference between the vapor pressure of the solvent and solution. So vapor pressure lowering is a colligative property. That means this property is totally depends on the number of solute particle. That means as the number of solute particle increases, this vapor pressure lowering, that is it get decreases. That means more and more lowering is there. So vapor pressure lowering is the colligative property which depends on the number of solute particles present into the solution. Then we will see one by one in details. The second one is the boiling point elevation. You know the boiling point. And elevation means increases. Boiling point increases when we add the solute into the solvent. Suppose the boiling point of the solvent is 100 degrees centigrade as that of the water, which is the solvent. But if we add into the water some sugar, then what happens? The boiling point of that sugar solution increases, elevates. That means this boiling point elevation is the colligative property because it depends on the number of solute particles. So boiling point elevation is denoted by delta Tb, which is also the difference between the boiling point of the solvent and solution. But this delta Tb increases as the solute particle increases. So, the boiling point elevation is the colligative property. Boiling point means the temperature at which the vapor pressure of that liquid becomes equal to the atmospheric pressure. So, the temperature of the liquid where vapor pressure of that liquid becomes equal to the atmospheric pressure is called as the boiling point. We will see in details later. Now third one is the freezing point depression. Depression means lower down or decreases. Now this freezing point decreases delta T up when we add the solute into the solvent. Suppose the freezing point of water is 0 degree centigrade. We know that. But if we add some sugar into that, what happens? The freezing point decreases, means goes below the 0 degree centigrade, such as -10, -20, -30. That means there is the depression in the freezing point if we add the solute into that solvent. So the difference between the freezing point of the solvent and solution is given by delta T up, that is the freezing point depression. Now next one is the osmotic pressure. Now this osmotic pressure, now this increases due to the addition of the solute into the solvent. Now that is the fourth colligative property, which is all these properties, all the four properties depends upon the number of solute particles. So they are the colligative properties. So students, the physical properties of the solute, the physical properties of the solution that depends on the number of solute particles are called as the colligative properties. Now, while dealing with the colligative properties in this chapter, we have considered the non-electrolytes. Remember that the colligative properties of electrolytes having the different properties than the non-electrolyte solute. So in this chapter we have to consider only the colligative properties of non-electrolytes. And when we deal with the colligative properties of non-electrolytes of the solution, that solution must be very dilute. That means very dilute solution colligative property we have to study. And the concentration of that dilute solutions must be about 0.2 molar or less than 0.2 molar. So remember that in this chapter we have to study the colligative properties of the non-electrolytes having very less concentration, and that concentration is nearly about 0.2 molar or that is less than 0.2 molar. Now the first very important colligative property is the vapor pressure lowering or lowering of vapor pressure. It is also called as the lowering of vapor pressure. Now student, first learn about the vapor pressure. In the 11th standard, I taught you about the vapor pressure. Now what is this vapor pressure? The pressure exerted by the vapors on the surface of that liquid when equilibrium is established. How the equilibrium is established? The rate of vaporization and the rate of condensation must be equal. Then and then the equilibrium is established. So when there is the equilibrium in the rate of vaporization and rate of condensation, at that time the pressure exerted by the vapors of that liquid on the surface of that liquid is called as the vapor pressure. Now this is the figure. Here some liquid or solvent is taken. On the surface of that solvent there are the particles which first go into the vapor the liquid state after some time. When these both rates becomes equal, at that time the pressure exerted by the vapors on the surface of that liquid is called as its vapor pressure. But we have to study the lowering of vapor pressure or vapor pressure lowering. Now what is this vapor pressure lowering? If we add some solute into that solvent, what happened? The solute is non-volatile and non-electrolyte. That means non-volatile means it does not undergo into the vapor state at normal temperature. But when we form the solution of such non-volatile solute into the volatile solvent, what happened? Some of the particles of the solutes also there on the surface of that solution. But these particles do not get vaporized because the solute is non-volatile. At room temperature it does not go into the vapor state. So they remain on the surface and only the solvent particles undergo into the vapor state. So as compared to the vapors of the pure solvent, the vapors of the solutions are less because these solute particles are there on the surface which interfere for this solvent to undergo vaporization. So always the vapor pressure of the solution is always less than vapor pressure of the solvent by addition of the non-volatile solute into that. So when a liquid in a closed container, this is the bell jar which kept inwardly on these beakers containing solvent and solution. That is, it is the closed container. So when a liquid in a closed container is in equilibrium with its vapor, when the liquid in a closed container is in equilibrium with its vapor, means rate of vaporization and rate of condensations are equal, then what happens? The pressure exerted by vapors on the liquid is called its vapor pressure. Now this is the definition of vapor pressure. When liquid in a closed container is in equilibrium with its vapors, then the pressure exerted by the vapors on the surface of the liquid is called its vapor pressure. Now experiments have shown that when a non-volatile, non-ionizable, that means non-electrolyte, experiments have shown that when a non-volatile, non-ionizable solid is dissolved in the liquid, liquid solvent, that means when a non-volatile, non-ionizable solid is dissolved in the liquid solvent, what happens? The vapor pressure of solution is lower. The vapor pressure of solution is lower than that of the pure solvent. The reason is what? This solid particle interferes the vaporization of this solvent particle. So the vapor pressure of the solution is lower than the vapor pressure of the solvent. So experiments have shown that when a non-volatile, non-ionizable solid is dissolved in the liquid solvent, the vapor pressure of solution is lower than that of the pure solvent. In other words, the vapor pressure of the solvent is lower. That is very important. The vapor pressure of the solvent is lower by dissolution or by dissolving a non-volatile solute into it. First, the vapor pressure of the solvent is more. But after addition of the non-volatile solute, what happened? The vapor pressure of the solvent becomes lower, and because of the non-volatile solute does not contribute. What is the reason? The reason is that a non-volatile solute does not contribute to the vapor pressure above the solution. This non-volatile solute does not contribute, or they do not go into the vapor state of above the solution, and therefore the vapor pressure of the solution is always lower by addition of the non-volatile solute into the solvent. Now this is the very important property. Now how the delta T delta P, that is the lowering of vapor pressure is calculated. Let us learn how the lowering of vapor and how it is the colligative property, that is also shown by, that is the with the help of Raoult's law. Now let us learn, student, what is the formula to calculate the lowering of vapor pressure. Now you always write down the notes by taking the screenshots, and due to that what happened, your notes will be completed, and then after opening of the college I will check that notes of the every student. Now again see the student, why always the vapor pressure of the solution is lower than the vapor pressure of the pure solvent. Now vapor pressure of the non-volatile solute solution is nothing but the vapor pressure of that solvent over the solution. Now see, if P01 is the vapor pressure of the pure solvent, P01 is the vapor pressure, this P01 is the vapor pressure of pure solvent, and only this P1, P01 is the vapor pressure of the pure solvent, and P1 is the vapor pressure of solvent above the solution. That means it is the vapor pressure of solution, but as the non-volatile electrolyte, that is the solute, does not go into the vapor state, so the vapor pressure of the solution is nothing but the vapor pressure of the solvent over that solution. But due to the interfere of the solute particles on the surface, very less solvent molecules vaporize, and therefore the vapor pressure of solution is always low. So if P01 is the vapor pressure of the pure solvent and P1 is the vapor pressure of the solvent over the solution, then this P1 is always less than P01. So the vapor pressure lowering is given as, how we calculate the vapor pressure lowering? Delta P is equal to P01 minus P1, because P01 is greater than this P1. P01 is the vapor pressure of pure solvent and P1 is the vapor pressure of solution. You can call it as the vapor pressure of solution. Now why the vapor pressure of the solution containing non-volatile solute is lower than that of the pure solvent? That is the question. I already speak with you about this, but let us learn again why the vapor pressure of solution containing non-volatile solute is lower than that of the pure solvent. The reason is that because the vapor pressure of the liquid depends on each with which the molecules escape from the surface of liquid. How the vapor pressure of the liquid depends on which factor? The vapor pressure of the liquid depends on that factor, how easily the molecules of the liquid escape from the surface of that liquid. If more and more molecules escape from the surface of the liquid, definitely the vaporization is more, and therefore because the vapor pressure of the liquid is also more, so because the vapor pressure of the liquid depends on the each with which the molecules escape from the surface of the liquid, when non-volatile solute is dissolved into that, then if we dissolve the non-volatile solute into that liquid, what happens? In a solvent, some of the surface molecule of solvent are replaced. If we dissolve, when non-volatile solute is dissolved in a solvent, some of the surface molecules of the solvents are replaced by the non-volatile solid molecules as shown in that figure. Now, what happened? Due to that, what happened? As the solute particles that contributes surface of that solution. Due to that, what happened? These solute molecules do not contribute to the vapor because they are non-volatile. When we add the solute into the solvent, what happened? Some of the solute molecules replaces the solvent molecules on the surface, and the solute molecules do not contribute to the vapor above the solution. Thus, the number of solvent molecules available for vaporization per unit surface area of solution is less. The number of solvent molecules available for vaporization per unit surface area of solution is less than the number at the surface of the pure solvent. The number of molecules available to undergo vaporization of that solvent is less than the number of molecules which are available on the surface of the pure solvent. And therefore, as a result, the solvent molecule at the surface of the solution vaporize at a slower rate as the solid particle replaces the solvent molecule. So, less solvent molecule undergo into the vapor state. And therefore, as a result, the solvent molecule at the surface of solution vaporize at the slower rate than the pure solvent. So, this results in the lowering of vapor pressure, and that is the reason why there is the lowering of vapor pressure of that solution than that of the solvent. Always P01 is greater than P1, and therefore P01 minus P1 is the delta P, which is the lowering of vapor pressure. Now consider the Raoult's law for the solutions of non-volatile solute. We already learned the Raoult's law for the solution of volatile solute. That means in that case, both solute particles and solvent particles vaporizes. There is the vapor pressure, total vapor pressure is the vapor pressure of the solute and solvent molecules. But now we have to consider only the Raoult's law for the solution of non-volatile solutes. Now here, in this case, the Raoult's law only depends upon the vapor pressure of that of the solvent. So what is the statements of the Raoult's law? That is, the partial vapor pressure is multiplication of the vapor pressure of that pure liquid multiplied by its mole fraction. But here there is no solutes vapor pressure, so it is applicable only to the solvent vapor pressure. So what is the statement now? In solutions of non-volatile solute, the law is applicable only to the volatile solvent and not the solute. And so the law states that, now this is the definition of Raoult's law for the non-volatile solute solutions. That is, the law states that the vapor pressure of the solvent over the solution is equal to the vapor pressure of pure solvent multiplied by its mole fraction. That is mole fraction of only the solvent in the solution. And thus, what is the mathematical expression of the Raoult's law for the solutions of non-volatile solute? It is only P1 is equal to P01 x1. Now, here there is no vapor pressure of the solute, so the mathematical expression of the Raoult's law for the non-volatile solute solution is P1 is equal to P01 x1. Here, P1 is the vapor pressure of the solvent, P01 is the vapor pressure of the pure solvent, and this x1 is the mole fraction of that solvent. Now let us calculate how we can calculate the molecular mass from that of the lowering of vapor pressure. Let us see that how it is calculated now. You can take the screenshot, students, of this blackboard writing, and you must write the notes, and always keep test book near to you, so that you have any the difficulties that you can see into the test book. Now this is about the lowering of vapor pressure, but we want to calculate the molecular mass of the solute from that of the lowering of vapor pressure. And how it is calculated? Let us learn. Now again, see students on the blackboard, pay attention. We know this, that is the vapor pressure of the solution from the Raoult's law is equal to multiplication of vapor pressure of your solvent into mole fraction of solvent. When we plot a graph of P1 versus X1, it is a straight line passing through the origin, because this is the equation of y is equal to mx. There is no intercept, so the graph passing through the origin. When we plot a graph of vapor pressure versus mole fraction, vapor pressure, here mole fraction increases from 0 to 1. In this way, as the mole fraction increases, that is the vapor pressure of that. Here we see the straight line of that. Now see here. When a plot of P1 versus X1 is plotted, it is a straight line as shown in figure. For a binary solution containing one solute, binary solution means there is solute and solvent, one solute and solvent only. So the binary solution containing one solute, what is that? The summation of the mole fraction is always unity. We know that is X1 plus X2 is equal to 1. Suppose we have to calculate this X1, then what we do? This X2 goes here and 1 minus X2. So X1 is equal to 1 minus X2. Now on substituting this in this equation of P1 is equal to P01 X1, the value of X1 as 1 minus X2, what we get? We get P1 is equal to P01 in bracket 1 minus X2. Now on calculation of this, P1 is equal to P01 into 1, P01 minus P01 into X2, P01 X2. Now, if we have to calculate this, that is the delta P, that is the lowering of vapor pressure, what we do? Subtract this P1 from this P01. So, if we take this P1 to this side and this P01 X2 which is minus to this side, that becomes positive. So here is the P01 X2 and the P1 is subtracted from this P01. So P01 minus P1 is equal to P01 X2. This becomes plus now because that goes to that side, and P1 becomes minus because it comes to this side. So this is the P01 minus P is the lowering of vapor pressure, and this is equal to P01 X2 we obtain. But P01 minus P1 is equal to delta P, that is the lowering of vapor pressure, and therefore delta P is equal to P01 X2. This equation, X equation we obtain as delta P is equal to P01 X2. Now as this X2 is the mole fraction, which depends upon the number of particles of the solute, X2 is the mole fraction of solute, then what this equation shows? This equation shows that the lowering of vapor pressure is directly proportional to the number of solute particles. And what this shows that? The lowering of vapor pressure is the colligative property. Remember that. As the lowering of vapor pressure depends upon the mole fraction of the solute from this X equation, we can say that this lowering of vapor pressure is the colligative property. They may be asked into the examination, show that the lowering of vapor pressure is the colligative property. Then you must show from this the Raoult's law. Then you must give this equation X, and we can say that the equation X shows that delta P depends on H2, that is the mole fraction of the solute, and this directly says that the delta P, which depends on the number of solute particles, and therefore delta P, that is the lowering of vapor pressure, is the colligative property. Now let us learn again one of the property, that is the relative lowering of vapor pressure. We are interested in the relative lowering of vapor pressure. Then what is the statement or definition of relative lowering of vapor pressure. Now this is very simple. Relative lowering of vapor pressure nothing but it is the ratio of lowering of vapor pressure to the vapor pressure of pure solvent. That is delta P divided by P01. Now see here, the ratio of vapor pressure lowering, that is the lowering of vapor pressure of solvent divided by the vapor pressure of pure solvent is called relative lowering of vapor pressure. So relative lowering of vapor pressure is given as, it is the ratio of lowering of vapor pressure and vapor pressure of the pure solvent, that is delta P divided by P01. But what is delta P? Delta P is nothing but the P01 minus P1. This is the lowering of vapor pressure, and this P01 minus P1 upon P01 is the relative lowering of vapor pressure. Now we know from the X equation that delta P is equal to P01 X2. This X equation, delta P is equal to P01 X2. So substitute the delta P here as the P01 X2. What we obtain? On substituting this delta P as the P01 X2, this delta P as the P01 X2 divided by P01. Now this P01 get cancelled here. What is remaining? Only the X2. Now this P01 and this P01 get cancelled. Here only remaining the X2. So X2 is equal to what then? Now this is nothing but the X2, that is the number of solute, so mole fraction of the solute. So X2 is equal to this relative lowering of vapor pressure P01 minus P upon P01, which is the relative lowering of vapor pressure. Now what this shows? The mole fraction of the solute. Now this relative lowering of vapor pressure depends upon the mole fraction of the solute. So relative lowering vapor pressure is also the colligative property. So the relative lowering of vapor pressure is the colligative property because relative lowering of vapor pressure is nothing but it is the mole fraction of the solute, and so relative lowering of vapor pressure is also the colligative property. Now let us learn, student, how we can calculate the molar mass of the solute from this lowering of vapor pressure and relative lowering of vapor pressure. Now let us learn that. Now students, we learn that is the how we can calculate the molar mass of the solute from that of the, that is how the molar mass of the solute is calculated from the lowering of the vapor pressure, that we will see into the next lecture, and also we will see the numericals on that. Now if students, you understand very well what is the lowering of vapor pressure, how it is calculated, what is the relative lowering of vapor pressure, and how these relative lowering of vapor pressure and vapor pressure are the colligative properties, that means they depends upon the number of solute particle, then you can like, subscribe and share this video to the other students so that they also get benefit from that and they can write confidently that is their answer into the examination. And if you like this video, you also subscribe that and watch this video very carefully and write down the notes. Thank you for watching this video.